Welcome back, everyone. So we're going to have the third lecture by Andrea Montanari today. All yours.
Okay. Thanks for the introduction. Thanks to everybody for showing up at the third lecture. And yeah, so what I talk about today is based on some work that we did a couple of years ago with Michael Celentano and Chen Cheng. After writing this paper, Michael left academia, went to OpenAI. And no, it's okay. It's not causal. And then Pier Francesco, who is a physicist in Paris. Well, where we left yesterday, we were looking at training a two-layer layers neural network. Okay, so this is what it is. Throughout this lecture, I use M for the neurons because that is what we used in these papers. And we are training for square loss, square test train error, and we are interested in square test error. And I tried to describe in the context of single index model. Some of the things can be made more general, but let's fix this for simplicity in the context of single index model. So y x is standard Gaussian, y is a function of one-dimensional projection of x plus noise. We discussed two theories. One is feature learning. The weights wi align quickly with w star, and there is no overfitting. And the neural tangent theory, in this case, the weights change minimally. They basically don't align to w star. The model is a kernel machine. It is linear in the yi, and there will be overfitting. In particular, the network will interpolate the data. And what I left with in the last lecture was this puzzle where if now capital N is the same as lowercase m. Sorry. If I look at the test error, at convergence or whatever after at convergence as a function of the number of neurons that I use in my network. With the standard initialization, He initialization or Lecan initialization, what's important is the scale, is not the distribution. What happens is that with one neuron, the neuron kind of align very quickly with W star, and so it learns the features, and the test error is nearly zero. With a large number, a sufficiently large number of neurons, and we try to quantify this. And okay, we don't have tight bounds, but the risk in the end is strictly bounded away from zero for any positive target, right? For any non-polynomial target. Here, in my example, the target, the single index model nonlinearity was equal to the activation function. This simplifies my analysis. Okay, so the risk is asymptotically the projection on sigma onto orthogonal to polynomial of degree L in the space, real line L2 space, real line with the Gaussian. Okay, so for any polynomial sample size, this is much worse than this. Okay, so what is the conclusion that we should draw from this fact? Is it the conclusion that large networks are necessarily bad, and then overparametrizing them dramatically is necessarily bad? Okay, so I'm not gonna hold the suspense more. I'm gonna give you the spoiler and explain where is the culprit here. And the culprit is really in this specific choice of the initialization. That is also the standard choice of the initialization in practice, the one that you find in PyTorch, etc. And this means that what in particular, what's important about this initialization is it means that the neural network has a very large Rademacher complexity at initialization. It has a very large L1 norm of second layer weights. Okay, and what I'll try to argue, so in this lecture is that if you start with this initialization, then you see this phenomenon. So if you start with the second layer weight of order square root of m, you get this phenomenon. The network gets worse with the width. If in contrast you take the second layer weights of order 1, okay, so the total L1 norm basically of order 1. Again, my normalization is that this is 1 over m, or I 1 to m AI sigma. Then the risk remain, I mean, we don't know what it is very precisely, but to leading order remains 0 at all size. Okay. Yeah. I think so. I think so. If you apply it, I mean, I think so. I'm fairly sure that it is this way. If you do this way, we proved. I mean, I didn't prove it to you, right? But if you believe these theorems that I stated, then this is what's going to happen. Now, I must confess that before waking up this morning, since this is not the first time I say this story, I told myself I should really do some simulations, right, for next time I say this story. But yeah, next time you hear me saying this, I promise I'll have also simulations. But if you believe these theorems, I mean, for this case we have simulation. Right? That's very simple. It's 1 neuron. Okay, this is quite easy to do the simulations.
Is the same as
actually, we have okay, not exactly in this setting, but we have some simulations that show it doesn't. They are not plotted this way, but kind of match with this picture.
M is the same as capital.
Yeah, M is the same. I apologize. Throughout this lecture, M is capital N. I'll try to use a M in the previous letters section. I was using.
If the Lorod initialization is the lazy limit, but that has 1 over square root of b in as the standard deviation. But then there is this a timing age which has 1 over square root of b in plus b out.
Okay.
And that I think should be the mean field.
But d in is still M, right?
So I guess as long as p is 1 homogeneous, then
right.
you'll have a 1 over square root of initialization for the second layer.
Okay. If it is 1 homogeneous, it changes, right?
Yeah. So like overall scale.
Yeah, perhaps for 1 homogeneous. Yeah. Yeah, I'm thinking of generic non-homogeneous. Yeah. Okay, so first of all, as I say, I'll try. So this thing, so when I use that specific single index model, I don't use it here. This is very generic. That the risk here is bad is very generic because I described the analysis of the neural tangent model and the kernel method associated to it, and that you get this bad error up here that holds for any function, actually any function in L2. The analysis here, the theorems that I know are for a single index, right? But I would think that boils down basically to analyzing the population landscape. And so if you have K matches to K, then, I mean, there are results of that type, that if you have, a K index model and then you have order K neurons, then, you can basically learn it well, you can align, etc. Now, are there results exactly in the same setting as gradient flow, etc.? Not precisely, right? So this is why I picked the single index, because I'm sure that, in that case, I'm not cheating. The two ends of the curve are, exactly in the same setting. For what concerns this curve, again, here there is no difference between the two scaling because m equal 1, so these two are the same, obviously. So these two, for what concerns here, well, Yeah, I mean, there is a piece of it. I mean, actually, this fact that I said I'll try to convince you of this, but actually, you know, it's not fully rigorous. There is one part of the analysis that is not. Okay, so because of that, I prefer to say not fully rigorous things in as limited cases as possible. I think it can be made for fully rigorous. It's just a matter of sitting and spending enough time on it. There is one kind of analysis exercise. Other questions? Okay, so there are three parameters throughout the rest of the lecture. Three parameters really to keep in mind, right? Or I always think of large N, M, and D. There are three parameters, control parameters that are very important. One is the training time, right? One is the overparametrization ratio, that is N over MD, right? Number of samples under over number of parameters, right? And the third one will be the scale at second layer weights at t equals 0. So the typical size of this AI. Okay, these are the three important parameters. And just to list the generic question that in the real world I would like to understand is, okay, these are four of these questions. One question is, okay, for instance, we know that if the model is overparametrized, probably it can interpolate the data. Neural tangent theory tells us some conditions under which it interpolates the data, but these are not the sharp conditions. So what are exactly the region of alpha and A0 under which you really interpolate the data? Once you do this, do you get a model that gives you good generalization? How these two relates, the lazy training overfitting and the feature learning no overfitting regimes that I described before. And how does eventually the generalization error more generally depends on the control parameters that I described before. And okay, to answer or to try to get at least heuristic answers to these three questions, I'll proceed in two parts, and this will be 2 parts of the talk. I'll derive a theory that is, what physicists call a dynamical mean field theory of this training that exactly captures the asymptotics n and d goes to infinity with n over d going to some alpha bar. And then I consider the limit m and alpha bar going to infinity with alpha bar over m going to alpha, right? So this is not, as I said, I want to keep alpha equal n over md and n md going to infinity. So there are many ways of letting this tree go to infinity, and keep this constant. I'm going to take a very specific one. It's an open and interesting question to understand. If you take this limit in other direction, do you get the same in other ways? Do you get the same theory asymptotically, right? Or the same, at least the same qualitative picture asymptotically. I mean, this limitation is dictated really by the kind of analysis that we do. Okay, so the dynamical mean field theory. So now this is a parenthesis. It's purely technical. So I want to describe a little bit what this is about. It's convenient to think of a slightly more general setting in which we have a generic risk function. We have xi's that are IID vectors, and we have a risk function that depends on 2 low-dimensional projection, 2 m-dimensional projection of the xi, theta star dot xi, and I think of theta star as fixed, as my ground truth, and theta transpose dot xi, and this is my parameter that I want to optimize over, and there are some noise parameters, epsilon I, noise variables, right? And then I run a gradient flow, and okay, here I wrote it a little bit more generally that what we really will use here, in the sense that I added the linear term. You can think of this as weight decay term, right? So we do the analysis, the general analysis with decay. So you can of course embed or encode our problem to layer neural networks with k-index data in this framework, simply by taking theta to be the D by M matrix that contains the M weight vectors, and theta star the matrix that contains the k vectors, and then all the others are 0. And sorry, this should be W star k. And then the loss function will be evaluated at R, U, epsilon will be the evaluation of the network on Ri, and then the evaluation of the response. Okay, so this is just a more compact than writing all this business that is a bit messy. Okay, so now I give you what the MFT is. It gives me a process, actually a pair of stochastic processes in M dimension. So you should think of M as much smaller than D. So for simplicity, you might want to think of M equal 1 first, okay? M equal 1 is a perfectly interesting case already. So in this case, this gives two stochastic processes in M dimension, and the stochastic processes are given by the solutions of these differential equations, the stochastic differential equations. Let's parse this equation. This is the derivative of this curly theta. Okay, there is a linear term in theta. Then there is a memory term that is also linear in theta. There is something that depends on this other variable theta star. And then there is noise. And this noise is drawn from a Gaussian process with a certain covariance matrix. And then there is this other stochastic process. Well, this is nonlinear. There is a memory term. There is something that depends on the loss. And then there is another Gaussian process with a certain covariance. So you solve these equations. You generate U and W. You solve these equations. So if somebody gives you this function gamma, C, CL, C theta, RL, R theta, and the other R theta, then you can solve this equation, and this defines a certain stochastic process. Now I didn't fill it in, but you should think of these 6 functions as solutions of some fixed point equation. So there is a set of fixed point equations that I'll write in a few slides. You solve them, you get this 5 function, and this defines the stochastic process. Okay. Yeah.
Physically, what do they mean?
Okay, so now what do they mean? So I have a high-dimensional process, a d-dimensional process here. Think of M equal 1. This is a d-dimensional process, and then there is a one-dimensional process. So what is the relation between this var theta and this capital theta? This is a vector, and morally, what happens is that this defines, characterizes the asymptotic. So in which way? Okay, perhaps I skip the assumptions. It characterizing the asymptotic in the following sense. So let me write it informally, and then perhaps you can read the equations after. So what it's saying is that if I fix a coordinate, right, of my high-dimensional process, fix a coordinate, and look at the trajectory of this. This is a function, the trajectory between time 0 and time t. Okay, so fix coordinate 300 and look at it between 0 and capital T, right? So this will be some trajectory. It will be a random trajectory, right? And now, okay, perhaps I'll write it, I'll draw it in blue. And now I have my stochastic process that I defined before, and I look it between time 0 and time t. So this is, I don't know how to do the curly theta. This is my curly theta between 0 and t that was defined by my SD. And the claim is that these are the same, have the same distribution, the two trajectories. Well, not the same, but the same asymptotically. So as, let's write it like this. So the distribution of these two processes is the same. So if I want to compute, for instance, what is the expected value of the maximum of this, I don't know why I might want to do that, but let's say I want to compute the expected maximum of theta I t between 0 and t, right? Let's say theta I t for t between 0 and capital T. I claim that this, as t goes to infinity, as n and d go to infinity, goes to expected maximum of my curly guy. Yeah, for every I, but that's trivial, for instance, in the case of this thing, because things are exchangeable here. So all the coordinates in this model, sigma covariance are, Gaussian. We do it a little bit more general by Gaussian, but various coordinates are exchangeable. Now, okay, I should correct myself. There is really the theta star, right? There is the ground truth, right? Yeah, so you have to write, yeah. So, okay, if there is a ground truth, you should, okay, perhaps now I get to the formula. If there is a ground truth, then the correct way to look at it is the following. You look at any function of, okay, first of all, I made a mistake. I have to rescale this thing by square root of d, because the coordinates of these are of order square root of d. So you take the trajectory of the I coordinate, you look at it between 0 and capital T, you scale by square root of d. You also look at the ground truth on coordinate I scaled by square root of d, and then you take any function, any reasonable function, and reasonable here means continuous in this space. And then you average this function over t or d, and the limit is given by my process. For instance, I can compute what is the fraction of coordinates such that the maximum of theta it is bigger than 15. Okay, exactly. Okay, one simpler example is that you can compute 1 over d, sum over I, 1 to d. So take the function psi to be psi of xy 0t to be x minus y times t. Okay? So this will become this, and then there is the square root of d that becomes d, and then theta star I minus theta it square. Okay? And so this d simplify. So this is theta star minus theta t square. Right? And the theorem says this, as d goes to infinity, this converges, d and then goes to infinity. This converges to the expectation of theta star minus this calligraphic theta t square. Here there is no I, sorry. So here there is no I. This is, okay, so what is this curly star? The curly theta star is just a variable that has the same distribution as the empirical distribution of your ground. Okay, so you have to assume, for instance, you initialize. So you have an initialization, you have a ground truth, and the initialization is, for instance, you can take the coordinate of the initialization to be IID with some law jointly with theta star I. But anyway, this is not very important. The important thing is that this thing gives me a way to compute basically all quantities like this, all quantities that are average over all coordinates of a function of my thing, or compute the empirical distribution of that. Yeah. P-limit limiting probability. So this is this plus or minus epsilon. This is, so this is given by this up to small law of 1 in probability. Sorry? Well, this I here is really a typo. I'm sorry. So this I here is really a typo. So there is no I there.
Why are you able to remove it?
Well, there was no I to start with, right? And so the assumption, so what is this bar theta? Oh. Oh. Okay, this here the technology is beyond me. Okay, what is this? Okay, I should explain. What is this bar theta star, right? So what I assume about the ground truth, right? So remember, in my model, there is a true vector, right? What do we assume about this true vector? I must assume that somehow it has some, I'm considering sequence of instances that diverge in dimension. So I should assume something about this true vector. So the assumption that I'll make is that if I look at the empirical distribution of the entries of these vectors, so 1 over d, sum over I 1 to d, delta theta star I. Yeah, so this is the empirical distribution, a distribution that puts mass 1 over d over each entry of this. As d and then goes to infinity, this is the law of a certain random variable. I call this random variable theta. Okay? And this is what entered there. And what the theorem says is that if that happens, then the joint law of the truth, and let's say, to be definite, let's say I look at the gradient descent or the gradient flow iterates at time t, at a fixed time. I look at again 1 over d, sum over I 1 to d at a fixed time. This is a probability distribution in 2 dimensions. It's a random probability distribution because these guys are random, and it's a probability distribution in 2 dimensions. This converges to the law of this bar theta star and this process bar theta at time t. Now I brought something a little bit more complicated than that, and wrote that this is not only true for a fixed time, but also if you look at the whole trajectory. Right? Perhaps I shouldn't have done this because it's more confusing than anything. But yeah, super.
That
It's for the Zoom, I think. But hello.
yeah. So in general, it seems that some kind of exchangeability automatically appears.
Yeah. I mean, one part of this is that the model for my features, for my feature vectors xi, is exchangeable, right?
Right.
So particular, okay. So here I'm taking, I stated it for Gaussians, right? We can do the standard model of random matrix theory, and you can do a little bit more with the change of variables. You can do something like this. We can do. Okay, the theorem will become a little bit more complicated. Perhaps let's not go into that. But the theorem implies something about also non-exchangeable entries of this matrix. Matrices like, okay, I'll tell you, sigma 1/2, so xi equals sigma 1/2 zi, and zi is an independent entries, right? And then you have to, you have to assume something about the joint convergence. So now you have sequences of matrix theta, and the ground truth theta star, and you have to assume something about the joint of this, the joint empirical distribution.
Sir, how robust is that mean field asymptotics to, let's say, non-Gaussian assumptions on the distribution?
Yeah, so as I said, I mean, the theorem actually is stated for Gaussian, but you can make it, it actually applies, the real theorem in the paper applies to any xi in this form, right? Where the zi's have independent entries, let's say sub-Gaussian, and they have all zero mean and variance, same variance, right? Now, of course, I can easily build, for instance, it doesn't work for orthogonal invariant sample, but there will be a variant of this that holds for orthogonal invariant sample. It doesn't work for very sparse matrices. That will be more difficult. It doesn't work for, I mean, I can give you a dozen examples in which it doesn't work, but here I'm interested in solving, this very simple, single index model, and even, or k-index model, even that is currently, I mean, this is not the bottleneck for solving. Okay. So as an application to two layers network, concretely, this implies things like this. If you look at the evolution of the weights and the evolution of the projection of my weights over the ground truth, and then the second layer weights, as n go to infinity, all of these converging probabilities to some deterministic functions. These are random functions. These converge to some deterministic functions, and these are the unique solution of some DMFT equations. Now, so far, I kind of avoided telling, so if you can solve this DMFT equation, you know the asymptotic learning dynamics, okay? And by the way, we made this rigorous, but people used this before us to write papers also in the machine learning literature, physicists. Okay, I didn't, I shied away from writing the DMFT equation for a reason, because they are kind of somewhat ugly, right? And they are ugly not just because there is a bunch of them, they are ugly because they have the following form, right? These are equations in these unknown functions, and already it's ugly the fact that you have to solve these equations for some functions. This is a pain, right? But the other reason why they are ugly is that how you compute this function. So you should think about this as a fixed point procedure. Start with some R and some C's, solve the stochastic differential equation, get the process theta and R, and then plug it here. And for instance, you compute the covariance of theta, and the covariance of theta gives you C. Okay? So it's a kind of fixed point in which you plug C here, you get the process, you compute the expectation, and you get C back, right? And why this is a pain? This is a pain because even evaluating this equation, just doing one loop in this fixed point procedure, requires to compute this expectation. And this is, okay, this specific expectation is not too hard because actually this is a Gaussian process, but this expectation is a pain, right? Because how do you do it? You have to, for instance, generate many Monte Carlo copies of this and whatever, right? All right, so this is why, okay, this is a little bit disheartening, right? All right, so this is the end of the first paper, and so this was a couple of years ago, and with Pierfrancesco, we had this idea of, okay, for the moment, we don't know how to solve these equations, even numerically, right, or do it efficiently, but we can do what physicists do, right? We replace it with something simpler, right? And so we did a Gaussian approximation on this equation, and I'll try to describe the nature of this approximation and the quality of this approximation. There is no rigorous result about that, other than empirically, you check that it works quite well. Okay, so this is a Gaussian approximation, but is not Gaussians appear everywhere, but this is not Gaussian process regression, and we are not approximating the stochastic processes by Gaussian processes. This is a disclaimer. What we are doing is the following. Think of this risk function, right? I want to think of it as 1 over n times a sum of squares, right? So times the L2 norm square of a certain function of theta. The function of theta is this function. As component I of this function of theta is just yi minus f xi theta. And here I'm abstracting away what are I and yi and xi. I'm simply saying this is a random function of theta. This is perfectly correct. Okay. So this is a function of theta. And now what I'm going to say is that I replace this function of theta by a Gaussian process, fg of theta, with the same mean and covariance. And then I'll do the dynamics for this model. All right. So here the hope is that by keeping the second order statistics of this f, notice we are keeping the second order statistics of f and not of f squared. This is very important. Then you can preserve a lot of the properties of the model. All right? And it's not hard to compute the mean and covariance. For instance, if you compute the covariance, just the covariance of this piece, well, it's not hard to show that this has this structure. Theta is really W's and A, and the covariance is a sum over I and J, AI and J, and then a function of the inner product WI and WJ. So it's a kind of messy covariance, but it's something that you can write down. Okay, at this point, the nice fact about this is that now the DMFT equation become simple. So they are not simple in the sense that there's few of them, but they are simple in the sense, because we write here for the full neural network model, which is a little bit of a mess, but they are simple in the sense that there is no more this problem of having to compute expectation with respect to this unknown stochastic process. And this is complicated. This is completely explicit equations in this. These are integral differential equation in this function C and R and C prime, R prime, etc. Right? So it's just about, they are integral differential equations. So if you look at one of that, this gives you the derivative of the, of respect to time of C, and then there is a certain function, another function, and all of these are completely explicit. Nothing is given in terms of an expectation with respect to an unknown process. Right? So this is what the Gaussian approximation buys it. Now we can at least hope to plug them in a computer and solve them, at least at reasonable scale. So just a quick parenthesis, there is this kind of idea was actually inspired by a simpler model that, let me describe it in spend a minute describing it. It's in a sense, it's a purely mathematical model, but I think it's a very interesting model. And this was first studied by Fyodorov and then Pier Francesco, and we came to it from another different perspective or different motivation. And the problem is the following. Say that you have, so the problem is, let's say, solving random equations. You know that if you have, the equations in the unknowns over the complex field, you can always solve them, right? And so Smale, sometimes in the 70s, asked the following question: can you solve them in polynomial time? Okay? And of course, this is in worst case is difficult. But Smale said, okay, what if the coefficients of these equations are Gaussian? Can you solve it? And this is stated as his 17th problem, a problem for next century. Okay? Solving And okay, this took some 30 years, but a few years ago was solved. Actually, you can solve efficiently the equations in the unknowns with Gaussian coefficients in polynomial time. Okay, so once that is solved, the natural question is what happens with equations over the real field. Okay, so one way to write it is that you want to solve f1 of theta equals 0, fn of theta equals 0, and it's convenient to sit in a compact space, so I'll take theta to be. And what does it mean that these have Gaussian coefficients? Well, you could think, for instance, that the phi of theta is sum over J1, JK, G I, J1, JK, theta J1, theta JK, where the G's are Gaussian, IAD Gaussian coefficients. And so you say, okay, I'm studying the problem of solving n homogeneous polynomials, Gaussian polynomials, over the unit spheres in the variables. Well, another way of stating this is that the FIs are Gaussian processes with covariance in this case, the covariance you can compute it is just theta 1, theta 2 to the k. And you can, of course, look at more general inner product covariances. Okay, so the problem that we studied with Deliran and that was studied in physics is the following, right? You have, n Gaussian processes on the sphere with covariance that depends on the inner product, so they are rotationally invariant. How do you solve them? How does gradient descent perform? Is there something better to do than gradient descent? Okay. And okay, so there is an interesting story there that I will not say, but yeah, you can look at the papers. And this I see it's a kind of a toy version of this neural network model. In both cases, in that case, one way to try to solve it is to do gradient descent with respect to the sum of the square of the FIs, right? Which is exactly what we are doing here. Okay. So in this paper about neural networks, what we do is that we study this system of equation. Okay, to simplify our life, we take a symmetric initialization. So all the second layer weights at initialization are equal, and all the first layer weights are the standard initialization that is uniform on the sphere. We compute numerical solution, and we try to guess the asymptotics as m goes to infinity and t goes to infinity. Right, now I'll show, perhaps before that I should stop and ask if there is any questions, because I'll show a bunch of results or things that we find out.
So did we resolve the grad L transpose issue?
Yeah, we solved it in the sense that now there is no more expectation of that type to be computed. Really, it's everything is as I said, completely explicit. The DMFT equation for this simpler model doesn't have
the Gaussian approximation thing.
Yeah, the Gaussian approximation.
Thank you.
Questions? Yeah.
Good an approximation is that?
This is an excellent question, and the answer is that I don't know. But I'll show you some simulations in which I compare to actual gradient descent of neural network, and it works well. But I don't have any rigorous results.
I think this is relatively similar question, but is there any heuristics for what kind of rates would happen for the asymptotics?
The asymptotics of what?
The rate at which it converges to the mean field limit.
Well, the theory to the mean field limit, yeah. I would expect at least one, this convergence here, right? okay, look at this convergence here. The convergence here will be CLT, right? So this will be 1 over square root of n or 1 over square root of t, right? So you cannot hope to get anything better here. And I would expect that at least for finite amount of times, you get the same convergence. Actually, I think, yeah.
Right, thanks.
Probably, yeah. Okay. There are simpler dynamics for which the 1 over square root of t kind of rate is known. By the way, okay, over dinner I heard, the other day that some of you know about approximate message passing, etc. The way we prove this is we show that this, gradient descent can be reduced to approximate message passing. So you can think of gradient descent as, performing, running a certain approximate message passing, algorithm and then doing some preprocessing. So for proving this theorem, we use the general theory of AMP. And so these equations are just quote unquote, but are some kind of rewriting of state evolution for this modulo, a bunch of change of variables that is a little bit crazy. Okay, so I'll start the results with dynamics in pure noise. So what does that mean? I don't have any single, so the phi function is 0. I don't have any signal, right? So this means that the xi are random and the yi are just Gaussian noise. It's from a machine learning point of view is not interesting, of course, but it's still an interesting optimization question. I'm trying to interpolate noise with gradient descent converge. So I'll show a bunch of figures like this. So these are solutions of the numerical solutions of the DMFT equation for increasing values of the number of neurons. Here we go from 8 to 2 to the 16. And here what I'm plotting is the prediction for a training error as a function of time. And here I'm taking this kind of standard lazy initialization, right? And in these simulations, I'm keeping this AI fixed. In this computation, I'm keeping the AI fixed. So AI are not optimized over. I think this is instructive for reasons that I will explain, right? And so what you observe is that in this limit, so first of all, the risk converges to a limit. This limit is given by one of these curves for each m. And then if you take the limit, this limit, we take it, we take several m at alpha constant, at overparametrization constant. So as the overparametrization, as m goes to infinity, as the width goes to infinity, you see these converge, they seem to converge to some limiting curve, master curve, that is this one. And then the transition between, this early time regime is ruled by some other scaling curve. Here we plot the same data as a function of t times m. They again collapse on another curve that is up here, and this means that there is another scaling limit here. So this plot says that there are 2 time scales in this phenomenon. There is a time scale of order 1 here, and then a time scale of order 1 over m. It is very fast. So very fast it decreases a little bit, and then there is a long plateau, and then it goes to 0. Right? The kind of plateaus that you see often in machine learning. Now, in this case, it goes to 0, meaning that the training error goes to 0, meaning that you will interpolate. Okay? Do you always interpolate, right? So this depends on, do you always interpolate? At first sight, you might say yes, because as m goes to infinity, the number of parameters becomes humongous, so you might have many more unknowns than variable. But you remember what matters for interpolation is really the Rademacher complexity of the network. And if you remember, the Rademacher complexity is basically, once you scale things, is basically this proportional to this gamma. So on this scaling, the Rademacher complexity is of order 1. So you expect what? You expect that if gamma is less than a certain critical gamma, okay, you expect this if you are able to do optimization perfectly, but let's just make a leap of faith. If gamma is less than a critical value, then gradient flow will not converge to 0. And if gamma is above a critical value, then it will converge to 0. And this is the gradient, the critical value for interpolation under gradient flow. Right? And it's expected to have the same order, that is order 1, as the Rademacher complexity bound. Rademacher complexity gives a bound of one side. Okay. So is it really of order 1? Can we compute it for our equation? So here we computed it in this way. We observed that when this guy converges to 0, it converges exponentially. So there is a well-defined relaxation time to 0. And what we do is basically we plot the relaxation time. This is the relaxation time versus alpha or versus gamma. The plot will look similar for various values of the other parameters. And you see that the relaxation time at a certain point diverges. And we conjecture that the point at which the relaxation time diverges is the interpolation threshold. So basically what happens is that, if your gamma is small, your complexity of the network is small, you don't converge to 0 risk, you converge to a positive risk. If it is large, you converge to 0 risk. When you converge, you exponent takes a well-defined time, and as gamma decreasing, this time grows and grows and diverges at the interpolation threshold. And if you fit the divergence, you get a power law behavior with an exponent that looks to be 2 here. This new looks to be 2. And from this, we can compute very precisely. All right? So there seems to be, open problem, a sharp phase transition between interpolation and not, with a critical behavior at the field. Right. So now this is if gamma is, second layer weights are kept fixed. This is the easiest case. What happens if we leave them free to evolve according to gradient descent? Something very interesting emerges. Let's start and, let's initialize them at something of order 1. So that the Rademacher complexity at initialization is very small, right? What happens is that second layer weights grow as a function of time. All right? And here are 2 plots, depending whether I plot in log scale or not log scale. If we plot on log scale, this emphasizes the fact that they seem to plateau at a certain point. And if you look what is this point, this is a point at which the network is able to interpolate. So you start with small Rademacher complexity, and what happens is the second layer weights grow, the Rademacher complexity of the network grows until it arrives at the threshold at which it's able to interpolate. At that point, it will interpolate and the risk becomes 0. The whole picture is very intuitive, right? And there is an interesting, as a function, on which time scale this happens on a slower time scale than before, is a time scale of order n. So I'm plotting this versus t divided by m, and these curves collapse on a limit curve, and also on this plot, they collapse on a limit curve. All right? So this phenomenon is ruled by a scaling function that says that a is square root of t times a function of t over m. Right? It has also, quite interesting behavior at 0 and in infinity. This function at infinity seems to go to the interpolation threshold. At 0, it goes to a linear function, so it has a linear slope at 0. And actually, if any of you is into spin glasses, these coefficients at 0 as a meaning in spin glass theory is what's called the threshold energy of a mixed p-spin model. It is a kind of classical quantity in spin glass theory that kind of emerges not mysteriously. There is a reason. But the main takeaway here is that, the complexity of you initialize the network with a small complexity, the complexity slowly grows until the interpolation threshold. So you always interpolate if you let second layer weights above. And this is another interesting plot where we plot, here what is this? The energy as a function of time But what's more interesting is the energy as a function of gamma, basically the Rademacher complexity. With time, the Rademacher complexity grows. So the curves go like this. You start this, and then you start here. This is for, again, for different time. You start here, and then you quickly go basically to this master curve, and then you slowly go to zero. So basically, you quickly minimize the energy conditional on the Rademacher complexity, and then the Rademacher complexity slowly evolve, and then the train error decreases to zero until here you interpolate. Okay, so all of this was under this kind of pure noise example, but I think this is the right, it's very instructive to then understand the case for with a single index model with some signal. Okay, so now data will be of this form. Okay, and okay, I'll give a one figure summary that is the same figure that I showed on Monday. Okay, so in this figure is the typical evolution of three quantity. The first one is the same as gamma of t, right? So there is on time scale of order 1, this remains of order 1, but then on time scale of order m, this starts growing and eventually becomes of order square root of m until you reach interpolation. So this evolution of the red curve is the same basically as we saw in the pure noise model, right? Rademacher complexity grows until. But then there is another, thing that we can plot here. I mean, we can plot the train error. Again, here the behavior is very similar to the train error to what we saw before, except that there is this first phase, but it goes to zero only when the Rademacher complexity becomes large. But then we can plot the test error, and the test error decreases and then follows the train error until time scale of order square root of m, and then the two diverge dramatically, and this starts to increase, right? So this regime is no overfitting regime. You reach basically the base error, and you learn the latent direction. And I mentioned it, this is captured by the mean field theory that was developed in this paper. In this regime, you unlearn the correct direction, the latent direction. You have overfitting, the train error goes to zero, and eventually here the test error is the same as test error of the best linear model of the data. Okay, so those were solutions of the equations of the DMFT equations, and here is a comparison with SGD experiments, and so here we're just running gradient descent, actually not even gradient flow, and actually we run stochastic gradient descent with some step size schedule. So in a sense, this was a really adversarial setting, right? Because it's not gradient flow, it's not gradient descent, it's stochastic gradient descent, and the step size is not kept constant. There is some variability, and despite this, okay, the points are the simulations and the curves are the theory, and you see they kind of match pretty well. This is train and test error, and there is this phase in which they are similar, and then the two of them diverge, and the point at which diverge gets later and later with the width of the network, right? And so you see really in the data this phenomenon where the test error first decreases and then increases again. Okay? And this is second layer weights that first are of order 1 and then become of order square root of m. Okay, and the relation between these two again is very easy to understand in terms of the Rademacher complexity bound that I described in the first lecture. This overfitting, this generalization error is upper bounded by basically the L1 norm that we are seeing here times 1 over square root of m. So as long as this is of order 1, there will be no overfitting whatsoever.
So question. Sir, are you comparing the mean field theoretical result with the running experiment with a stochastic gradient descent?
So
Yeah,
this
the graph is not clear. Which one is the theoretical mean field?
theoretical is the curves, right?
Okay.
And the points are, so the
I see.
theoretical area is DMFT, and the points are simulation for SGD. So there is a discrepancy here. This discrepancy can be due to the fact that we are doing SGD and not gradient flow. Can be due to the fact that we have a step size schedule, a learning schedule that is not constant, and then can be due to the Gaussian approximation. And okay, we didn't investigate in detail. So I guess if we did a more friendlier setting, we would get a smaller error. But still, despite all of these approximations, these changes, okay, I find it surprisingly good. I was really stunned of seeing this figure. Yeah. So the curves are Gaussian, purely theoretical, purely Gaussian approximation. And the points are non-Gaussian, real neural networks with whatever number, 2 to the 9 neurons, etc. SGD, finite step size, so very different setting. I mean, I think that we could compute curves like this, modulo, using sufficient number of GPUs to solve these equations, right? I think we could compute them, but these curves are computed quite efficiently, quite quickly. Those would take substantial.
And all of this is for the single index model, not the pure
all of
noise.
this is for indexing.
Quick question. The insight regarding the increasing width, does the point at which the divergence happens between the train and test, does that happen earlier if it's wider or later?
It's later when it's wider. Okay? So this is this point at the scale, the time scale at which overfitting happens is of order m. Right? While the time scale at which fitting happens, learning happens, is of order 1. Now, all of this is done within this case, this setting in which n over md is kept constant. So m time scale of order m is equivalent to saying time scale of order n over d, n over d. Right? So n over d is proportional to m. Okay? So you might want to think of this as more intuitive. Huh? Somehow this is saying that as the sample size over dimension gets larger, then overfitting happens later and later. And this makes a lot of sense, right? Okay. Thank you. Yeah. I don't think so, because here you see that, okay, there are a few things, right? Because there is the dimension, and then there is the target function, the number of parameters that you need. And then there is the class that you are fitting by, etc. Now, I'm not saying that this is the ideal, the optimal way of fitting these functions, right? This single index model. If I know that the model is a single index model or a k-index model, and I'm trying to find the statistical optimal way, I wouldn't use a very wide neural network, right? I would use probably a neural network that is width proportional to the k of the k-index model. So let's say if it is a single index model, I would use a neural network with width of order 1. Or perhaps I would use an even smarter non-parametric method. Okay? Here, really, the focus is trying to understand the dynamics of this method on this simple example. Okay? Okay, so there is something. So most of this is non-rigorous, but it's a few things that we can prove. One thing that we can prove is a lower bound on the overfitting time scale. That is okay under some regularity condition on sigma and on phi. If you start with a bounded initialization, right? So small Rademacher complexity, then the following happens: the norm, the infinity norm of second layer weights remains, doesn't grow too fast with the time. And then, this is a constant, this A1 is a constant. And as a consequence, the risk, the generalization error, so the gap between the population error and the empirical error is bounded by something that grows at most quadratically with time, the classical square root over the over n factor. So this, in other words, says that as long as this is much smaller than square root of n over d, then you are in good shape, okay? So the error is small. In other words, this is saying that the overfitting can only happen when t is bigger than n over d to the 1/4. Now I say that the heuristic thing is n over d. What we can prove really, and this proof is relatively simple, is n over d to the 1/4, but it points in the right direction. Other thing that we can prove is that in this first time scale, when there is no overfitting, the dynamics is captured by the classical mean field asymptotics. This is something that we worked a few years ago. Okay, I wrote equations for this, but these are deterministic equations for the AI and the projection on the weights of the second layer weight on the target dimension. So the AI and the projection on the target direction. You can write a set, closed set of equations for this function. You can think of these equations as describing gradient flow with respect to the population risk, and then making the high dimensional approximation that Wi, Wj is equal just to the projection Vi, Vj. So basically, if you take two first layer weights, the component orthogonal to the target direction of these weights is are basically orthogonal. So these weights remain random in the orthogonal direction to the target. So basically orthogonal between them. And all that matters is the projection to the target. So I wrote these equations in full generality, but under symmetric initialization, this is a two-dimensional dynamics. So it's relatively easy to analyze. All right, so these are again, so what we can prove here is that this equation captures, so as I said before, we can show no overfitting, we can prove no overfitting up to n over d to the 1/4, if I'm correct, if I remember correctly. Now we can prove that mean field theory is correct up to log n over d to the 1/3, okay? Now this is much smaller, of course, than n over d or n2 over d over 1/4. So there is a big gap between this and what is conjectured to be true, but at least we show that there is a divergent time scale at which there is no overfitting. So this is all controlled by the difference between the AI and the mean field AI is the ideal one. So this is all consistent with the picture that we came up with. And, again, very similarly to what I described before in the case of pure noise, there is in this system a slow variable, in this dynamical system, a slow variable that is, again, the second layer weight, the total norm of the second layer weights, that here is written a square root of m, which is also the Rademacher complexity. And to show that, here we plot the generalization error, so test error minus training error, as a function of Rademacher complexity, basically. And what we see is that, the curves for different m have to be read in this order. So what you see is that the curves for different m, they basically collapse on a limiting curve. And the limiting curve is basically the generalization error of the model trained with lazy initialization without updating second layer weights. Okay, so basically there is a fast evolution towards constant Rademacher complexity and then a slow adiabatic evolution of the Rademacher complexity. And this demonstrates this feature unlearning phenomenon. Here we plot again, this is again the plot of the Rademacher complexity, and here instead we plot the projection of first layer weights on the target direction. And what happens is that it first grows, so this is the feature learning, the weights align with the target, and then it decreases at the same time scale at which this starts to increase. All right? So the network is trying to just fit the noise and is starting to ignore the signal. Any question about this? Okay, so that's everything that I wanted to say. I mean, there was, you know, for me in my mind, there was for a while this puzzle of how there is this neural tangent regime in which, you know, there is overfitting. The overfitting is benign, but statistically the model, the neural network performs very poorly. And then this feature learning regime in which there is no overfitting and the neural network performs statistically well, right? And how these two fit together. And now it's quite clear there is a kind of clear picture of how this fit together, right? It depends on two factors, right? The initialization and the time, right? If you initialize with a very large initialization, you never start with very complex network, high Rademacher complexity, you will never see feature learning. We only see overfitting, benign overfitting potentially. If you start with the small initialization, then you will see the two, but you will see the two on two different time scales. You first see the feature learning, and then if you keep training and you don't regularize, you eventually interpolate the data and see overfitting, right? Now, 1 year ago, or say 1 year ago, I had no clue about this, and was very confused by this. But now, at least at the heuristic level, the picture is quite clear. Thank you.
Questions?
Can you explain that lower bound time again once?
So this is saying that this theorem. So you say, okay, there is a time, TLB. So LB because there is a time at which overfitting start to happen and which mean field asymptotic start to, standard mean field asymptotic start to fail, right? From the heuristic analysis, this time scale is of order basically n over d or of order m, which is the same in this case. Now, what can we prove about this? We can prove that it's no smaller than the minimum of log m to the 1/3 and log n over d to the 1/3, right? So up to that time, this simple asymptotics works fine, and it works out fine in a quite strong sense, right? Now, there is a big gap, of course, between log n over d and d, and in that case, this asymptotic seems to be correct empirically or semi-heuristically, but we cannot prove. Here, the proof is very simple if you look at the paper, so there is a lot of space for improvement.
For the NTK limit, the Rademacher complexity is high.
Right.
And for the mean field limit, do we know that the Rademacher complexity is low?
Well, here on this scale, the weights of second, again, here we are a little bit using, we should be aware that we are using a little bit on overloading of terminology because Rademacher complexity is always over a function class in theory, but here we are looking at a specific network. So, but if we call the L1 norm of second layer weights to be the Rademacher complexity in this regime that is, you initialize it to be of order 1 and stays of order 1. And this theorem proves that, theorem before is that it stays of order 1 or stays much. Okay, sorry. The Rademacher complexity is of order 1 over square root of whatever m, right? And it stays of order 1 over square root of m up to some time that here is n over d to the 1 quarter, right?
And so in the NTK regime, we saw both benign overfitting and maybe catastrophic overfitting, where like the test error was very high.
Well, I mean, I think, okay, so I must say I didn't follow the evolutions of this terminology, but in a sense, this is still benign overfitting, right? In the sense that if I let the sample size go to infinity and I keep interpolating the NTK, you reach 0 error eventually. The only thing is that you reach it very slowly. It's the same in the in the Peter paper, right? Peter Bartlett paper on simple linear regression, where they coined this terminology. What they proved as benign overfitting is that the error goes to 0. The prediction error goes to 0. It goes to 0 really slowly, right? Here also it goes to 0, but it requires sample size that is eventually exponential in the dimension. Right? So it keeps decreasing. So the way it decreases is according to this staircase that I showed yesterday, in which every time you increase the sample size by a power of t, it goes down by a factor.
So it's a somewhat broader question. Does this tell us something specifically about the network architecture and the basis of functions that we're using to perform fitting? Or do we want to think of this as a very general result about you could have used some other basis and it would have been easy to generalize these results?
It's not clear to me what does it mean basis of function here. This function space is not linear, right? So what does it mean?
Did the proof not require the fact that you had a specific architecture for the network that you are using to perform the fitting? If I'd used some other architecture, so by basis of functions, I mean you use a different architecture, a different basis of complete basis of functions to perform fitting. And then one could ask the same question.
So this is for 2 layers neural network with. There is no assumption really on the activations. I mean, there is some generic kind of, as you see, Lipschitz assumptions and boundedness assumptions on the activations, but otherwise it's a 2 layers network. Now, do I believe this phenomenon might be more general? Perhaps yes. I tend to believe that, this fact that, a short time you don't do overfitting, and the longer time you do overfitting, and if you have enough parameters, sooner or later you interpolate, and if you interpolate, it must be that the Rademacher complexity of the network grows in some sense until you overfit. I think this might be more general, but formalizing it is a good question. Right? What is really the slow variable, and how this relates to complexity? These are all good questions.
Do you think a similar analysis could be done for like 1 layer transformers or?
Yeah, I mean, could be done for, I think that, okay, to move to something more complicated, frankly, I mean, okay, so here we follow this DMFT path, which is very nice in the sense that you can solve this equation, get nice curve, plot them, see what's happening. Before plotting these curves, I was a little bit lost of what would happen, right? Now I have an intuitive picture, right? And now what I would go about is these curves contain a lot of details that I don't really care too much about, right? So, if I had to go to a more complicated architecture, I would try to prove something very basic, right? Try to identify what is the slow variable, right? Try to see how this controls generalization and prove that this evolves slowly, right? That this grows slowly. This is what we how this theorem goes. This theorem doesn't go through all the DMFT business that is very difficult to analyze, mathematically. It goes just, bounding, we know a priori what is the result, right? And then we say, okay, we know that there is what is the picture, what is the slope variable, and then we try to bound the growth of the slope variable. We know that this controls complexity, right? So some kind of analysis of that, would be interesting to do to more complicated architecture.
Because the reason I was asking was because there are like bunch of results, as you saw, for like especially one layer transformer, they do this, do that, but this kind of complete picture is not there yet, I think. It would be good to have something,
Thank you. If there are no more questions, let's take Andrea for this great series of three lectures.